In Chapter 5, we're going to be working with rational functions, and we're going to start off with inverse and joint variation. Now, you've already done direct variation. Direct variation follows a linear model. So if you think of the differences, direct variation looks like this. They all involve a constant of variation, but direct variation is y is equal to a constant times x. Inverse variation would be the inverse of this, which would be inverting x, the constant divided by x. The constant of variation is this k value, k, and in all of these, k stands for the constant of variation. And when you look at joint variation, normally you're going to add more variables. So a standard sort of direct type of joint variation, z would be equal to k times y times x. But joint variation can take many different forms. You could have something like z varies directly with x but inversely with y, and it would look something like this. So we'll talk about more types of variation as we go forward. So this is your vocabulary for this section. You need to know what inverse variation is and what it looks like. That this value k is called the constant of variation, and joint variation in the standard form the book's going to talk about is z is equal to k times y times x. And the big difference here is it's introducing a third variable. So direct variation was something you studied previously. We're now moving into inverse variation and joint variation. A problem that you might want to use inverse variation to solve in a real-world sort of application is this idea that you're probably very familiar with, that the size of a storage space, in this case we're talking about an MP3 player, it can store a certain number of songs based on the size. If you increase the size of the file, then the number of files is going to change, and this is inherently an inverse variation model. So what's typical in inverse variation is that as one variable increases, it causes the other variable to decrease. So as I increase the size of my file, the number of files I can store in a given space decreases. So later in the section we'll go ahead and we'll solve this problem. Here again is the concept of inverse variation. Y is equal to, in this case they called A the constant of variation. Typically a constant is represented by k, so typically you'll see me talking about k, but it doesn't matter if we identify it A or if we identify it as k, it's constant, right? Its value does not change. We may change x and that will consequently change y. Okay, so if you want to take a look at which type of variation is it, you would want to put it back and compare it to the forms. And again, I'm going to go ahead and switch to A. So y is equal to a times x is direct variation, and this is inverse variation. So if we want to take a look at these, if we put them in the form y equals, in this case I'd divide by x, so this would be 1 over 5x. This would be inverse. If you take a look at this guy, this is neither, right? There's no multiplication going on. There's no constant of variation, so this one would be neither. This is in fact a linear function, but it's not really either. And in this case, if I multiply it through by x, I'll get y is equal to 8 times x. This would be an example of direct variation. Okay, so this one's neither due to the absence of the constant of variation is not 1. That means it's not really going to change anything in this particular case. Okay, so to practice identifying inverse and direct variation, go ahead and work on problems 7, 8, and 9. Please remember again that in a direct, again to reiterate, in a direct variation model, as x increases, y increases. And in an inverse model, as x increases, y decreases. Okay, and the converses are also true. As y decreases, x decreases, y decreases. and in the inverse model as x decreases, y increases. Okay, so in this case, both variables do the same thing. In an inverse model, they do opposite things. So go ahead and do these problems and come on back to the lecture. Okay, so if I want to write an inverse variation model, it's the same sequence of steps that we would use if we were writing a direct variation model. The only difference is that we'll use y is equal to, again, I'm going to use a divided by x. I normally think of it as k, but that's all fine. I want to match the book. So if I take the supplied values, 9 is equal to a divided by 1, I'll find that the constant of variation must be equal to 9. So if I want to write the model, y is equal to 9 divided by x. This would be writing an equation that relates x and y. It's important also that you think about the concept that this type of a problem, it tells me the variables vary inversely. That's what tells me to use the inverse variation model. It says use the given values to write an equation relating x and y. Okay, so that's what I've done so far. I've written an equation that relates x and y. And see, it says then find y when x is equal to 3. We're going to talk a lot about how you read problems, but this word then, that means that I have to supply two answers. I do this item, this task, and then I do another task. So to solve this problem, it's going to require two answers. Then it wants me to find y when x is equal to 3. So if I take 3 and plug it in for x, so I'll have 9 divided by 3, y would be equal to 3. This is my second solution to the problem. I bring this up because it's very common for students to not do the second task or to not do the first task. Okay, so what's important is that you go through, and this requires two answers, an equation and a value of y. So it's very important that you read carefully when you're looking at the instructions on a problem. Same sort of problem, I'm going to do this again, same two steps. Y is equal to, right, in this case y was 2, it would be equal to the constant of variation divided by 7. When I multiply through by 7, I'll get 14 is equal to the constant of variation. And when I write my model, y is equal to 14 divided by x. That's one solution. Then find y when x is equal to 3. So y would be equal to 14 divided by 3. That is my second solution. Okay, so this is what these sorts of problems look like. It's going to look the same way when we do joint variation. We're going to use the model, plug in our supplied values to write an equation by finding the constant of variation. So I find the constant of variation, and the constant of variation has to go back into the model. Okay, it does not say in this instruction, find the constant of variation. I did do that because I had to do what they asked me to do, write an equation that relates x and y. That's what this is. Okay, so make sure you do that when you work on these problems. Do problems 16 and 17. When you're done with that, come on back to continue the lecture. So one of the things that you would need to do in working with variation in a practical application setting is you need to be able to tell the difference between the two. So when you take a look at input-output tables, typically this is the way you might be supplied data, collected data, whether you're looking at whatever type of variable you might be looking at. We could be looking at price reductions versus sales. We could be looking at a lot of different things that we represent x and y. But once you have the data, knowing how to interpret the data to select the correct model, and we're working with a lot of different models in the course of this class. We've worked with quadratic models, we've worked with exponential models, we've worked with power models, we've worked with a lot of different types of models. The key for you in leaving this class is being able to understand that when you're looking at sets of related information, how do you look at that information and determine what type of a model do I use for it? So there are some clues when you're talking about variation. if you look look at my data table, you see that my x values are increasing and my y values are increasing as well. This looks like it's direct variation, so it might be direct. I know for sure it's not inverse, because if x was getting larger, then y would be getting smaller, and that's not what's happening. Okay, so I know it's not inverse variation. So when you think of checking a data table, we're really now talking about the constant of variation. So if I take the inverse model and I solve it for the constant of variation, I'll get y divided by x is equal to the constant of variation. So if I have x's and y's, if I find a constant, meaning the same value, right, then I know that this would be a direct variation model. I know for sure it's not an inverse variation model, but if I take 132 and I divide it by 12, 132 divided by 12 is equal to 11. And 198 divided by 18 is equal to 11. And 253 divided by 23 is equal to 11. And 319 divided by 29 is equal to, guess what? 11. And 374 divided by 34 is equal to 11. So I know that the constant of variation for this model is 11. If I then want to write the function, I know that y is equal to 11x. This would be the direct variation model for this. So I use the base form to solve for the constant of variation, and this is the mathematical function I'm doing, y divided by x. When we look at our second data table, I see that my x values are again increasing, but you'll notice that now the y values are decreasing. This looks like it might be inverse variation. Remember, if I had tested this and these numbers had not all come out to be 11, then it wouldn't have been a direct variation model. It would have been some other sort of model, and I would have had to go on and check something else. Okay, so if we take this model, y is equal to a divided by x, and solve it for a, I see that x times y is equal to a. So if I do 1.5 times 40, 1.5 times 40 is equal to 60. And 2.5 times 24 is equal to 60. And 4 times 15 is equal to 60. 7.5 times 8 is equal to 60. I'm sorry, I said 60 and I wrote 16. I really don't know what I was thinking. 60. 10 times 6 is equal to 60. So I know that my constant of variation is 60. And if I put that back into this model, y is equal to 60 divided by x. Okay, so if I multiply my inputs times my outputs and get a constant, that's going to be inverse variation. If I divide my outputs by my inputs and get a constant, that's going to be direct variation. Okay, so remember again, if this had not turned out to be a constant number, then it would not have matched either of these models, and I would have said, well, it's neither, and I would have moved along. Okay, so go ahead and give this some practice. Do problems 22 and 23 from our exercises. Identify what type of variation you're looking at. Remember that before you start multiplying or dividing, you should go ahead and examine, are the variables doing the same thing? When x increases, does y increase or decrease? That'll help guide you which to do and get you to a faster solution. When you finish this, come on back and finish out the lecture. So writing a joint variation model is just, in terms of the steps, it's the same as writing an inverse variation model. We're now working with this formula, z is equal to a times x times y. But I'm still going to do the same tasks, and I still have the same challenge that it says write an equation that relates x, y, and z. And it says then find z when x is negative 4, and y is 5. So I still have 2 steps to do. So when I go ahead and put this into the model, I see that z, which is 24, is going to equal to my constant of variation times my x value times my y value. So I'll have 24 is equal to negative 12 times the constant of variation, and when I divide by negative 12, I'll get negative 2 is equal to the constant of variation. So now if I want to write the model, z is equal to negative 2 times x times y. This is my first solution. So I found the constant of variation, I put it into the model, or into the base model, to be able to write my model. And now I want to find z when x is negative 4 and y is 5. So negative 2 times negative 4 is 8. 8 times 5 is 40. Okay, so 2 separate solutions. One more example like that, I take z is equal to my constant of variation times x times y. So 15 would be equal to 3/4 times a. Multiply both sides by the inverse of 3/4. Remember, these will cancel and I'll just get a. So 60, 4 times 15 is 60, divided by 3 is going to be 20. Equally, I could take the 3 and cancel it with the 3 and the 15. 4 times 5 is 20. When I write my model, z is equal to 20 times x times y. That's a solution. And then when I plug in these new values of x and y, I have z is equal to 20 times negative 4 times 5. 20 times 5 is 100 times negative 4. Z is equal to negative 400. Okay, so in each cases I had 2 solutions, an equation and a number. Go ahead and practice that by doing problems 27 and 28, and come on back. So as I mentioned, there are a wide variety of different methods of variation. Okay, we've talked about some basic ones: direct variation, inverse variation, and a joint variation that is basically a direct version of joint variation. Just adds in, it basically is direct variation, adding in one more variable. So what's important is you get used to the idea of where do these things go when it's described to you. If y varies inversely with x, you see the constant of variations in the numerator, but because we have inversely, x has gone to the denominator of a fraction. If we say just jointly, right, that's the same as, really the same as saying directly, jointly, without any other sort of explanation. You'll see that they're in the numerator as well. There's no denominator because there was no reference to inversely. Okay, if we are talking about inversely with the square of x, now you see x squared is in the denominator. So inversely puts it in the denominator, and the square of x defined what it was. Z is varying directly with y, so directly with y, so y is in the numerator, and inversely with x, so x is in the denominator. Okay, so you'll notice that every time it says inversely, the item goes to the denominator. Inversely with the square of x. Inversely with x. Okay, in this last one, x varies jointly with t and r, but inversely with s, so you see s is in the denominator. Right? If it says jointly, right, we're in essentially the numerator. Directly also is in the numerator. Right? jointly with T and R. They're in the numerator. And the constant of variation, where is it? It's always in the numerator. Okay, so as you work with different types of variation, the language that's used in the problem is your guide for where the item goes in an equation. So it's very important that you read carefully and you think critically about what this information means when it's written out in English. Okay, so give it some practice. Do problems 31 through 33, and then come back and we'll finish out this lecture. Okay, so when we started the lecture, we talked about this idea that the larger, if I have a limited amount of storage space, the larger the items I'm storing means the less I can actually store. So that's, again, a case where my inputs may be getting larger. That makes my outputs become less. If the size of my file gets larger, the number that I can actually store in that space becomes less. So if I want to write a model that gives the number n of songs that will fit on the MP3 player, the important thing is I thought about this and I determined this is the relationship. That tells me it's inverse. Okay, and that's what's important, is that by reading this, it tells me right here that the number of songs varies inversely with the average size of a song. Okay, so inversely is the key. I'm going to use this model. I know that I'm going to work with y is equal to a divided by x. And they tell me that I can store 2,500 songs when the size of the song is 4 megabytes. So if I multiply both sides of the equation by 4, you can see that I'm going to get 10,000 megabytes is equal to my constant of variation. That would be the size of a hard drive, right? So it's a 10,000 megabyte hard drive. You wouldn't really have that much now, but that's the idea that we're working with. So now they want me to make a table. Okay, so if I want to write my model is y is equal to 10,000 divided by x. And again, it's megabytes because x is being measured in megabytes. If I want to make a table for x and y, I want to use 2 megabytes, 2.5 megabytes, 3 megabytes, and 5 megabytes. Okay, so when it's 5 megabytes, I can store 2,000. When it's 2 megabytes, I can store 5,000. When it's 2.5 megabytes, then I could store 4,000. And when it's 3, then I'm going to be able to store 3,333 songs. Right? So 5,000 songs when they're 2 megabytes, 2,000 songs if they're 5 megabytes. Okay, so that's using an inverse variation model. And you'll notice again, the characteristics are as x increases, y is decreasing. That's the sign of an inverse variation model. So that's section 5.1.